to let you go. Just like the wind, she slipped through my fingers, yeah. Just like the earth beneath fell away, and this blinding flash of memories played before my eyes, and all I saw empty hearts and neon lights. They're playing with my mind. Gotta get out of here tonight. Oh, I wanna run off and fly. And I'll tell myself it's fine to be alone, just to find somewhere that finally feels like home. Oh, oh, oh. I hate all this overthinking. Oh, 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 oh. The more I swim, the more I'm sinking. Take me to a world of silver. No more heartbreaks, tears, painkillers. Take me somewhere unfamiliar. Bring me back to where we started out. Get me out.
Hello, everybody. I am back after taking a break for the last, 10 or 11 days, more than the last week and last 2 weekends. Been pretty distracted. I've been working on some projects that I have on the side and had sort of not been dedicating enough time to them. Not that the streaming was really the main thing stopping me, but it's easier for me sometimes if I just focus on one thing all day, kind of. And then I'll to know, how much people are aware, depending on where you are in the world. I am from the United States, so I've been paying a lot of attention to what's been going on in the U.S. the last almost 10 days now, I guess, with very large protests against police brutality and the general structure and behavior of the police and their very violent reaction to those protests and the sort of rioting that has been around those. Although it does seem like the rioting has died down in recent days, which is good. And hopefully the police will lay off and let the protests happen, because what they are protesting about is very real. And at the same time, a lot of people have seen the behavior of the police in reaction to those. And, maybe they've come to some recognition that the police are prone to violence in a lot of cases. And they've shown that in these last few days. But in the instances that I've heard of where there was nobody protesting, or rather, where there was no police presence at the protest, things didn't get chaotic and it just sort of worked out peacefully. So, depending on how cognizant they are of those things, maybe they'll realize that, hey, if we don't show up in a bunch of riot gear ready to throw shoot tear gas and shoot, what do they call it? Rubber bullets, basically. I mean, bullets with a little bit of rubber on them, shotgun shells at people. And, maybe if we don't do that, they won't be antagonized and they'll do their protesting peacefully. That would certainly be my hope. And of course, at the same time, a protest that has no reaction is probably not one that gets a lot of attention from people. So they may not, there might not be a lot that comes out of it if people didn't, if there wasn't the police reaction that there was, especially from a media standpoint at the Washington, D.C. stuff, where it was the military doing it because they're not a state, so they don't have state police and all that. In any case, that's enough on the U.S. topics. I'm sure that some of you that might be watching are not from the U.S. and it's not really that it's not that important of a thing. But if you are from the U.S. or if you're just curious about it, I would encourage you to look online. Maybe not rely too much on the major news outlets, because they seem to have a very specific focus on what they care to cover. And there's a lot of evidence of police malpractice, let's say, out there online if you care to look for it. But on this stream, we're going to focus again on hacking practice, binary exploitation stuff. Before we get into that, I have just a quick programming note. I don't have the details right now, but I think I'm going to try to vary up my streaming a bit. So when I was streaming before, I think I went for, I don't know, like 2 weeks maybe straight every day, which is good. I'm going to try to keep with an everyday schedule again. But I think I'm going to vary the topics a bit and do maybe every other day do some binary exploitation stuff, continuing with the nightmare challenges until I'm through with all of those, or I guess until I get real bored with it. Depends. But I'll keep doing binary exploitation. I might just find challenges from some other location, some other source rather. But on maybe every other day, I will be working on some other projects. I want to build a decoder for x86 instructions. So something that, and I'll just transition here so we're not looking at the start screen still. So just a program that will take the binary machine code representation of some instructions and for x86 platform, and give back a data structure representing that sequence of instructions. There's a lot of potential ways to go about that, depending on, really what it comes down to is how are you using the output of that algorithm. If you are doing a disassembler, there might be certain kinds of analysis that you want to do, so you might need certain pieces of information from that stream of instructions, or a different kind of analysis would need different other pieces of information. If you are strictly printing them out with as little modification as possible, you might not need to have details about which processor state changes, like which flags get changed and stuff. You might just need an opcode name and register, memory address kind of stuff. So depending on what your actual use case is, you would want to transform the instruction stream into different pieces of data, different data structure on the output. Although it's still, effectively an array sequence, because that's a set of instructions is going to be a linear sequence. But there's definitely some room for different kinds of implementations, different focuses on the implementation. And my initial goal with working on that, which is I think the thing that I'll try to start working on tomorrow's stream, there's a couple different goals that I have. The biggest one is really solidifying my knowledge of the x86 instruction set, and in particular how it is encoded. So because it's such an old instruction set, and I'll get into this in the next stream, there's a lot of weird stuff that they did to fit it into as few bytes as possible effectively. So that makes it harder, more annoying to decode than maybe an ARM or RISC-V or something that's a newer generation, or just a newer design of instruction set. And then obviously being the complex instruction set, what do they call it? I think it's complex versus reduced. So CISC instead of RISC. And then having, multiple lengths for the different instruction sizes puts a lot of more complication in it than other ones necessarily have. So basically I want to get a more intuitive sense of how all of that works. And I think the best way for me to do that is to have to write some code that actually implements that logic of decoding the machine code instructions. And secondarily, I think if I can write it in C, I'll probably do it in C first. Then I would like to try re-implementing it in Rust as a nice project for helping me learn Rust. Because I've taken a very minor stab at that a couple of times using just like the tutorial materials, going through the Rust book, but the projects are very small in those, at least when I did them. And I find that the best way for me to learn a new language is to like have a real project to work on, and to, as I try to do a thing, then I'll research on, through Google or whatever, find, oh, here's how I do that in Rust. So the goal would be write it first in C, come to an understanding of what the program should be, and then rewrite it in Rust. So that I have a real world program that I'm working on, that I know what the goal is, what the implementation probably should look like, and then I can sort of have this comparative way of understanding Rust is like, okay, here's how I went about it in C, and here's how I went about it in Rust. So that's what I think I'll work on the next stream, and then probably the day after I'll come back to binary exploitation, and I'm thinking maybe on the weekends, at least maybe one day on the weekend, try to do some stuff on Try Hack Me. I think because people asked about that in chat. Certainly there's a lot of other people that do Try Hack Me stuff, but I think I should probably, I don't know, try to be more well-rounded, as they say in the US. Try to, expand my skill set beyond the binary exploitation and the low-level focus on that kind of stuff. It's not really my wheelhouse. I've done very minimal stuff related to, especially web kind of hacking, doing like recon and then finding, XSS or SQL injection, or I don't know. I don't think I've ever done like an SSR, server side, SSRF, I guess. And then there's like SSR, or server side like template injection or stuff. Like there's all manner of different techniques that come out because of the level of complication involved in web frameworks. So I think I'll give that a shot, or at least I'll go to Try Hack Me and I'll start go through boxes and see what's what I can start accomplishing, I guess. I don't know. Hopefully that'll be a little more accessible to people watching the stream. That's why I'll probably do it on the weekend when I think more people will be around or available to watch the stream. And yeah, so I'm gonna when I stop being so lazy, I'll try to put together a little schedule thing and have that on the Twitch channel page. And I think I'll also switch up my schedule so that I am streaming in the evening. It's the evening my time right now. It's about 9 p.m. here in Indochina time, which is like early morning in the US, depending on what coast you're on. And maybe hopefully is like middle of the day or evening, elsewhere in Asia and Europe. And so this might be a little more accessible to folks around the world, and I think I can make it fit for my schedule rather than doing it early in the morning. So that's all the programming notes for this one. No, I don't think somebody in chat saying, do I want to be famous? Can I? I don't know if I can just ban that account, but oh, I can see the users that are in chat. Interesting. Oh, they left already. Whatever. Okay. Interesting. Okay, so let's get to the binary exploitation stuff that we'll do for this stream. Previously, I have gone through this section all of these entries in the Nightmare course. I'll go ahead and throw that in chat in case anybody is interested in checking it out for themselves, and I should throw that into description as well, but for now I'll just leave it in chat and it'll be linked on the VOD. So yeah, we've gone through all the intro stuff, which is just reversing and some like intro to using the tool stuff. All the stack buffer overflows, of which there were many. A few format string ones, and then the array indexing, which had one that really hit me at the beginning, this first one, and then the rest were relatively more in line with the difficulty that I saw from the previous challenges. So we got through all of those, and now we are moved on to the category known as bad seed, which my guess, because when I click on the bad seed entry, it's just, it doesn't have a description for this category. What I'm guessing is that it is vulnerability is related to having a random seed that is, it's poorly chosen in some way. So the randomness is not as random as it should be. It's more predictable, and then you can take advantage of the fact that it's predictable. If you don't know, generally speaking, the way random programs work is or random algorithms within a program, they use what are called pseudo-deterministic, or rather, they use pseudo-random algorithms that are actually deterministic. They're not pseudo-deterministic. They are deterministic. They are pseudo-random because they are deterministic. And so, effectively, and this is the case for your cryptographic randomness as well, they have some amount of state where that's just any kind of data that's internal to the random number generator, and that piece of data is what is used to calculate the next random number to provide. Or in a lot of cases, it's like the next bit, whether it's a 1 or a 0. And the amount of that state is large enough that and is modified and used in such a way that it's extremely unpredictable. Given any small sequence of bits that you get out of it, you don't have much indication as to what the next bit is going to be. There might be some repetition in there, but whether or not the repetition continues on the next bit is just as difficult to determine as if it weren't a repeating sequence that you had seen before, basically. This is all, really high level over the mathematics of it, in part because I don't really understand the details of the mathematics, but the effect that you get when you use a random number generator algorithm, a pseudo-random algorithm, is you can't predict what the next number is, but if you had the exact same state, you would always get the same next number. This is really helpful, partly because the computer itself has very few sources of true, what they would consider true randomness. So you're just working on the basis of what little bit of random data you have acquired, but you might need to generate a lot more seemingly random data out of that. So part of the benefit is you don't need as much truly random data to make this work. And the other part is if you are developing an application that requires some amount of seemingly random behavior, and then you have a bug in your program, and it only seems to happen when the randomness works out a certain way, it's extremely helpful for the debugging process to be able to lock that down and have the exact same random behavior each time you run through the program. So this may not be what people think about as much when they're thinking about why we have a pseudo-random generator instead of a truly random generator. This is what I think about probably primarily because coming from a history of working in game development, there are lots of places where you want to use some randomness in your game development. Maybe not in the game logic. Maybe you have a completely deterministic gameplay, but the visuals might have randomness. You might have randomness in something that sort of sparkles a little bit or has like an effect. You want it to look a little bit, you don't want it to look very grid-like and patterned, basically. So you can do some randomness in there. And if that visual effect breaks every time when the random number generator hits this particular sequence, you don't want to have to like keep repeating the program over and over again until you happen to luck into that exact sequence again so that you can see what's going wrong. You want to be able to say, okay, let me run the program with this exact same sequence every time I want to run the program. And so that is a huge benefit to any program that has a randomness element, is to be able to replay the program with the exact same sequence of supposedly seemingly random numbers. And what this comes down to is what's called the seed to the pseudo-random number generator. It's an initial value that the program provides. And they give this value to the generator, and it's what sort of forms the basis for the state before the first number has been generated. And so if you start with the exact same seed, if you start with a seed of 1, and then on the next time you run the program, you start with a seed of 1 again, you will get the exact same sequence of numbers from the generator. They seem random compared to each other, but obviously they're deterministic because you can get the exact same sequence every time if you provide the same seed. So that's a long way of explanation to get to what this category known as bad seed is about. And basically, the idea is you've provided a seed that is actually not itself random enough. So when I talked earlier about the idea that there's like a few sources of truly random data that a computer has access to, usually what they do is they take that little bit of truly random data and use it as the seed for the pseudo-random generator. Because if you use a little bit of random data to start the seed, then you don't know where the state began with the pseudo-random generator. So you effectively have as long as your pseudo-random generator is quite good, has a high quality of randomness, and there's different ways of measuring that, I guess, but essentially if you're not using a very bad pseudo-random generator, then having that little bit of initial random data to kick things off is sufficient. But there's no restriction. You could use a fixed starting value every time. So again, you could use 1 every single time, and it's just not going to actually be random. A classic thing that has been taught in a lot of sort of programming tutorials and things that you would find if you are learning about doing random number generation is to use the current time as a seed. And this is thought like, oh, well, every time you run the program, the time is different, so you will get a different random seed and you're good. There's a few problems with that. One, the time is going forward, effectively at the same rate. I mean, the time moves forward at the same rate, obviously, and the way that clocks work on a computer, that's roughly the case as well. So you're not gonna have a random seed that is smaller than you had on the next run. You're not gonna seed it with a number that's smaller than the current one. I don't know that actually has any implications as to decreasing the quality of the random output that you get, but it's definitely, you're not giving it a random input is the key. The seed is not random if you're using the time, because time marches in one direction. It doesn't randomly skip back and forth. The more fundamental problem, though, and what is probably the case in at least one of these challenges, is that the granularity of the time that you are using might be too big. So if you are initializing, if you're seeding your random number generator with a time that is the number of seconds since the Unix epoch, which is like January 1st, 1969, I think, or maybe 1970. It's a specific date, and it's the key here is that it is calculated in number of seconds. Well, a second is a long enough time on a computer that you could run the same program a bunch of times. If it's a small program, you could at least start it a bunch of times within a single second. And each time you start it, it is going to have the exact same random seed, because the granularity of the timer that you are using to seed the thing is only on the per second. So, maybe seeding it with the time and using the millisecond time resolution thing is, or, nanosecond resolution clock that is available at least on some processors. Maybe that's a better way to go, but ideally you're using a source of random data that is just truly random. For example, in what do we want to do? Do this. Yeah, so we just got one block, I don't know, 115 bytes or something. So here we've read from /dev/random, and it's given us some amount of random data where effectively each of these bytes should be completely random. Each bit in this should be completely random, whether it's a 1 or a 0, because this is the place where you can ideally, it used to be not necessarily the case on Linux, but I think for a long time it has been the case that this is the device that you can read from, the sort of pseudo file to retrieve the truly random data that the computer has access to. That might be, it uses different input sources from hardware basically as its like way of getting random data. So timing related to when packets show up on the network, and I think if there was like a mouse and keyboard connected, probably timing related to that stuff as well. I don't know the details of where it's coming from, but it's effectively signals from the outside world, because you can't look elsewhere within the data in the computer. You can't look at the hard drive. You can't look at the memory, things inside of the CPU, and try to use those, mine those as random, because they're not actually random. They were the result of other calculations from the computer. And so the best place to get random data is either sort of timing from signals from actual hardware that is connected to the machine, or a device that is specifically designed to provide random data. So there are things that have like, I don't know, certain radioactive atoms, I guess, that they're able to measure through some physical setup how quickly their radioactive decay is happening, and the rate of that is random, so that translates into random output results. But those are very expensive devices. They're not in my computer, certainly. But yeah. So if you aren't using /dev/random as your seed for the pseudo-random generator, your source of randomness, or you aren't seeding your pseudo-random number generator with a truly random value, and that becomes potentially a security vulnerability, because it might be possible to figure out the pattern of random numbers that are going to happen with your program. And certainly there are real world cases where this has been a vulnerability that somebody was able to exploit. It doesn't sound like the kind of thing that I would try to exploit in the real world. And I'm not even particularly confident that I'll be able to solve the ones in this challenge, in the 3 challenges here. But it just feels like probably more mathy than I want to get into, but we'll see. I'm going to at least attempt them. So the program is called time, and I guess that might be an indicator that they're using the current time as the seed for the random number generator, which is again a very common sort of tutorial slash like thing that you might see suggested on the internet if you're just doing a very cursory search for like seeding or like how to generate random numbers in C. Yeah, let's look on dummies.com. So in here they call rand. They don't call srand, which is the seed, the random number generator function. So that's interesting. It's possible that there we go. Okay, so you don't have to seed it, I guess, but I don't think the C library itself will seed the random number generator on startup. So yeah, here we go. This is the thing that you'll see a lot. Let me zoom in on that, I guess. So their first example actually takes input from the user to be the seed value used. I mean, it's not necessarily wrong. It's just shifting the problem. Now whoever runs the program or however it is running is responsible for correctly seeding with random data, which is totally possible. You could pipe /dev/random into there and it would work, but you haven't solved the problem really. You've just shifted it. Here then, in their more truly random than ever choice, and this isn't necessary. Oh, that is the end. Okay. But what you see their use is srand, and they call the time function, pass in null. If you pass null to the time function, it's going to return the current time in Unix time, which is seconds since the Unix epoch. I'm pretty sure we could man page that. There's probably 3 times. So it's the same as get time of day, sure. And that good? No, that's onk. What? Okay. Yeah, seconds since the epoch. So 1970, January 1st. And yeah, they don't mention anything else in this. Now, granted, this was like potentially written a long time ago, but although I would wager that even when this was written, the deficiencies of this approach were known. My reasoning for saying that this is like a common thing is partly because I've seen it many times, and it was sort of how I was taught to do it, and the logic of using the time because it's going to be a different value every time you run the program was what I was also taught. And it wasn't until years later that I found people explaining how that is not necessarily true. And there are definitely better ways to go about it. So my point in doing this search is simply to, and I apologize for, so they're doing the same thing here, is to just show how common it is that they will tell you, exactly the same problem here on C++.com. They're not necessarily saying this is the thing to do, but this is the example they're giving, and this is the example you'll see everywhere. So it's the kind of thing that you will, I would wager that a lot of people programming C would think to do this first, unless they are in the category of people that have had to think about the security implications of it and have taken the time to learn about how to do it better, basically. So, okay, I don't need the walkthrough. But we can check out the main function in radar. And yeah, we didn't have the C code for this, so that's fine. We can look through the code. There's a guessing game. So, okay, before we get into actually the output that is presented with puts, we've got here a call to time with 0 as the first parameter. So that's us getting the current time in seconds since the Unix epoch, and then we move that and make that the first parameter to srand. So we are we're doing exactly the thing that I was talking about. We call srand time, and then we immediately call rand to get the first random value as a 32-bit integer, maybe 32-bit unsigned integer from rand. We store that, and then the program is going to try to guess, or is going to ask us to guess what that number is, I'm assuming. Let's see. So then it asks us to enter the number. We flush. And see, they make it real easy for us because we should be able to, we might not be able to do this with Pwn tools. The key is that this program will have to run in the exact same second at least twice, but we can definitely do it with C and just maybe call system. Maybe not. I think I'm going to try it with Pwn tools first just because it'll be simpler, but otherwise we need to run it, get the pipe, and then read the output. But basically what's going to happen is they're going to ask for our number, they'll scan it in with scanf, and then they tell us what our guess was, and they tell us what number they had generated, which is at local C. That's where they store the result from rand. And then they're going to do standard out for that stuff, or they're going to flush that data, make sure that it gets printed, and then they are going to compare our input against the random number that was generated. If it's the same, then they'll come down this path and call the give flag function, which presumably reads a flag in. We'll check that out in a second, make sure that I create whatever file it needs, I guess. Otherwise, we get wrong guess. So the strategy here is, again, the time function is going to return the same value every single time it gets called if we are in the same second when the program starts. So if we can start the program 100 times in 1 second, each of those 100 times is probably, potentially in the exact same second, so it has the same result from time. Obviously, depending on exactly when the computer's timer ticks over from 1 second to the next, some of those might be in 1 second, some of them might be the next second. You might have to try it a couple times. We only need 2 run-throughs to be in the exact same second, so I think we're fine on that. On that front. But yeah, we'll run it once, and then it will print out what its random number what its generated pseudo-random number was, and we will just store that, and then we'll run it a second time. Hopefully it's in the exact same second, and we'll guess that number for the second time. And because it just told us what the answer was. So if we can get it to happen fast enough, then our second guess will be correct, and we'll come down and we'll print the flag. So that's the strategy. I'm going to go ahead and look at the give flag function, which does open up this. It has it in a particular absolute path, which is great. So and I guess okay, so we got the flag in the spot where they want it. Not thrilled that it has to be at this particular absolute path, but that's fine. I can always delete it afterwards. So yeah, that's our strategy, and I'm gonna do it with Pwn Tools because I feel like we can get this going fast enough with Pwn Tools, but the reason I'm hesitating on that is if I scroll up before I did the clear, I was copying the time the challenge program out, and they had a solve program which was written in C. So maybe when they solved it, they needed to do it in C to get the speed necessary to make sure that the program was started twice in the same second. Although, like, what I would think is I can start two of them in Pwn Tools. It's just going to wait for input. So if I start them right away and then I talk with the first one, the other one's going to be sitting. It's already generated its random number. So that's one benefit that we have, is the random number generation happens right away. If they did it after the printf, or the scanf rather, so if they did it after waiting for our input, then I would maybe need to do it in C or something that would allow me to run the whole program and start the second copy immediately after and get that all happening in less than a second. But what I think I can do is just start two instances of the program right away, basically simultaneous, and they will both generate the same random number because they should be in the same second at that point. I'll run through one of them, providing a guess, and it's probably wrong. And then I'll read in what the right answer is, and then the second one I'll provide that as the guess. So let's get our script going. Got the binary. We don't really need any. We're not doing any fancy stuff with this one. No shellcode, no ROP, none of the more standard hacking stuff that we've done before. So I'm happy for that. Yeah, we're just going to start two processes. And proc 1 and proc 2. Proc 1, we are going to read until that is the prompt, and then 3, because that's a very random number, that'll be our guess, and then proc 1 dot read until looking for, and finally just call it R&D is proc 1 dot read until period drop equals true. So we're going to drop the period itself, and then we're just going to get that as an integer, base 10, and we will print that out. And then that's what we will guess for proc 2. We'll read until the prompt again. Send line R&D and proc 2 dot receive all dot encode, and we'll print that out. All right. Let's see. doesn't have an encode. Maybe I need to say decode. Yeah. Yeah, there we go. That worked perfectly. Other than I guess I need to update it. Pip3. Okay. So your guess was that, well, great. I've just decided to spam my screen with installation stuff. Why is it, oh, we had 401 and now, okay. What did we install a new version of Capstone? What do we have Capstone in here? 305 rather than, it had Capstone 401 and now it's installing Capstone, oh, 402. I see. It's just greater than or equal to 305. Whatever. Okay. I think we can just run it again and see the output. So random number that we got from the first process that we generated and ran through was this random value. Obviously 3 was not the right guess. And then the second time we guessed that exact value again and got it right, so it printed out the flag for us. So that's all we needed to do. Didn't need to write it in C, which is good because that would have taken me a while. Because I'm not that like up on the necessary stuff for getting a pipe or getting the right like file descriptors from a child process and all of that. So this one is, you know, the like super easy introductory version of this challenge. If you understand the mechanic behind why doing SRAND with time null as the seed value is the wrong way to go, then exploiting this particular program, or I mean exploiting is not necessarily the right term, but getting it so that you can guess the value that it has already generated is about as easy as this kind of thing could get. So cool. I don't think we need to. Oh. Okay. They took a very different approach to it, to solving it. That's why they have a C program. Not because they needed the speed of running the target program twice, but because they, I mean, I'm not going to go through all the details, but basically what they did was generate the same program rather than have it like prompt and do the guessing stuff. They just print out the random number, but they're calling SRAND times 0 again. So if you run their solution program in the exact same second as the time program, the actual challenge program, then they will both be generating the same random number. And so you can just pipe it in. So they call solve and pipe the output into time. So they are printing the same random number as the output for solve, which then becomes the input to the guess function with time. That's another great way to do it, because, you know, Bash is going to work fast enough to run both of these two processes in the exact same second, unless you have an extremely slow computer. Okay, so that works for me. Yeah, and this is, you know, I hadn't thought about going about it this way, but that's a smart way to go about it too. And would potentially be an easier way if they didn't have. So I was talking about how they're generating the random number up here. Oh, you know what? Their approach would still work if you were generating the random number down here. after the scan. Would it? I think so, because as long as you generated your random number, imagine they're generating the random number up here, basically, and then printing it as the input that comes to scanf. So as long as the code up here and the code down here run within the same second, then they're going to generate the same random number. So their solution would also be a very fast way to, or a very good way to solve the problem if they hadn't put the random number generation right away. Whereas mine, where we run through it, see the output where they print out what number was actually guessed or generated by the program, has more of a timing issue to it, I suppose you could say. And it also suffers from the fact that like it requires this output of looking for that number of like this is the bit where the program prints out what random number it actually generated. If they didn't have this, since that's, you could definitely write the program and not include that little bit, then my solution wouldn't work because we're relying on the program outputting the number. But their solution does not have that limitation. So potentially if the next problem, this Tux Talk Show program from HS CTF 19, from the high school CTF 2019, if that, is not printing out what something based on the random number it's generated, then we might need to do a similar approach where we happen to generate the number in the same second in our own code. That being said, it might also not be a program that is using the faulty logic of generating a seed or using the current time as the seed. So we'll find out when we get to there. What's this one called? Oops. And then modules. I'm getting a bit of a indication just from the fact that it does have a C program in there as well, that maybe they're in the same situation. We'll find out. That might be a good technique, even if you're not doing the time thing. If you just replicate whatever mechanism they're doing for generating the seed, if that seed generation is deterministic, yeah, you could do it. The one problem with this, of course, actually, now that I think about it, in a CTF, I don't think this would necessarily work, now that I think about it. So the setup in a CTF for a pwnable is generally that the program is running on some other machine. The program is running on that machine because the flag is sitting on that machine. If you were supposed to run it on your computer to get the flag out of it, then it would be more of a reversing challenge where the flag was hidden somewhere within the program. So what that means is that this solution only works if that other computer has the exact same, down to the second, timer setup, basically. Like their clock is at the exact same moment as our clock on our computer, down to the second, because we are going to generate a random number from the time on our computer when we run the solve program. And then if we pipe that through netcat to the program on the target machine for the pwnable, if it's generating a random number on that machine and that machine has a different time on its clock, then it's going to get a different random number. So I wonder if they mentioned that at all. Yeah, I don't see anywhere where they mention that this probably wouldn't work in the real CTF setup. So unfortunately, even though it's definitely a more elegant solution, it's not really unless you had a way to send your program to the target machine and then run it, in which case, you've got a lot more options available to you, perhaps. But yeah, I don't think that this would be a valid solution in the CTF that was going on live, even though it'll work when it's running on your computer locally, which is interesting because most of the challenges in this Pwnables category, you can absolutely just run them on your machine and get your exploit running and working properly. Usually the configuration differences between your machine and the target are not much of an issue. That might come down to like ASLR being turned on or off, but otherwise it's like the configuration settings are kind of what the binary has been compiled with, rather than, hey, what is the time of the clock on your machine kind of thing. So that's interesting to think about. And I wonder, since it seems like they might have taken the same approach with this one, if they've basically solved a simpler challenge than what was actually presented in the CTF. Not that it matters to me particularly, but I think it's good to keep that in mind, that actually what seemed like a very obvious solution, or a very like elegant solution, I'd say, because it wasn't obvious to me. It's not what I had thought of, but what seemed at first like a very elegant solution maybe turned out not to be a proper solution. All right, we're going to set up the flag file because this is going to print out the flag. If we do whatever with it, whatever we need to do to trick the random number generator. And this one is written with C++, clearly, from all that. So in the main function, we'll look at that first. Okay. Opens up the flag.txt, reads that in. We do the same time srand stuff. Interesting, okay. And then we print out, welcome to Tuck's talk show, enter your lucky number, use a cin with the int operator, and then we've got a bunch of data. That we are shuffling around, maybe? Or just, no, it's just copying it to another part of the stack. It looks like this is probably, at least some of these look like they would be got like, well, 6C, 614, 4E seems like it would be in the ASCII range, but that would make this 05, which is pretty low. Like that's, I don't think that's a nice printable number. So I'm not sure if these are ASCII characters or not. Let's see, and then we do something with that. I'll maybe get into reversing that in a second if we have to. And it looks like we probably have a loop that'll loop 4 times. No, 5 times. So we loop through this 5 times, doing some kind of division. Might have to just run this in GDB to figure out what the division is, but I've seen enough code like this to have a pretty good sense that the result is taking one number and dividing it by some fixed denominator for integer division. And this is just the optimized way of doing it without actually using the division instruction. So we put that into EAX and we turn it into RAX. and we use that times 4, so we're indexing into that with RBP minus 260. What would be at RBP minus 260? Oh, yeah. The 260 is like the start of the data here, I think. 264. Do you have anything at... Maybe it's always at least 1? I would think if... So it's a random number that we are generating, and then we're indexing in. And then what do we do with EDX? Maybe EDX is, oh, I see. Okay, so EDX is the random number divided by something. It looks like that might be the case. And then here we are indexing in to that sequence of bytes from up there that was hard-coded into the instructions. And we are subtracting something from the random number from that value and storing it back into that location. So we're sort of randomly shuffling this data. So I think the reason that we do this copying stuff is we have it sort of, I don't know, in a fixed original location, and then we copy stuff around. And what do we do with 288? So then, let's see, put zeros into those. We've got another potential loop here. Yeah, loops another 5 times. And just add these values up. Okay. Interesting. So there's definitely a case where we need sorry, my phone is like, I don't know if y'all can hear that actually, but it's just going off. Okay. Well, let's go ahead and run the program. I have some sense that like we've got a string of what I'm assuming are primarily printable characters, although not exclusively. And then we are randomly modifying those, and then we are summing them and comparing that sum against the value that we had guessed in the beginning. And if they compare equal, I guess we read the file. Maybe they're not equal. Right, yeah. So if they compare equal, then we go through this chunk, which I'm guessing like maybe 240 is where we stored the flag. Read this in what do we do with the flag.txt? Maybe 220 is where we store the file. I don't know. I don't know where we are storing the flag. I guess it could be. Could just be that we are, yeah, we're doing iStream, so we're like reading in from the file and then doing cout to like print out to standard out. So guess. So I mean, I think that's the success case, certainly. Okay. So let's go ahead and run it. It doesn't do anything. It doesn't print anything if we... Yeah, okay. Whew. So, I mean, we can know what the random numbers are going to be in the sense that if we can run the stuff ourselves. And if we run it in the same second as it's being run on the other computer, then you can get the same random number. The big problem with that, again, is what I was talking about earlier, is you are relying entirely on your clock being synchronized to the second with the remote computer's clock, which, since we're not running it on a remote computer, we can go ahead and sidestep that issue, but I think I would have more of an issue with this if I were solving it during the CTF. Or I guess basically I would have to have some mechanism by which to know the clock that was used, what the clock was set to on that remote computer, so that I could set my own computer to be synchronized with it. And that synchronization would probably need to be redone every so often, because our clock, there's a clock skew or whatever. So like over time, my clock would drift from their clock, and it might be more than a second off over time. I don't know how quickly that would, they would diverge. I don't know if it would be within an hour or more or something. I don't know what the real numbers are on how quickly computer clocks diverge, but it might be necessary to resynchronize as well. So I'm just guessing, like if I was actually at the competition, I would need to go talk to the people operating the CTF and get that info so that I could synchronize my computer, because I don't think that calling time on two different computers is going to automatically certainly give the exact same time. All right, so we need to reverse engineer this. So at 260, we have just the value 79. And then at 25C, we've got 12C9 7F. Okay. Let me do this. I guess we can give this a shot, and we can give this a shot in Python. I'm gonna call it solve.py, just like naming it after the solve.c that was used by the person creating the Nightmare course. Because I named the earlier one exploit, but it's not really an exploit. It is a solution of some kind, though. So let's just start with data. I don't know. And just filling in each of these. Uh, 056 C614E. Okay. So let me double check that, because this is how they are listed in this chunk, but then they are copied from those locations into the locations that actually get used. So 260 has what we have at 278. Okay. 274 is at 25C. That's fine. Then 270 is at 25.8. 26C is at 25.4. And 268 is at 250. And then lastly, 264 is at 24C. Okay. And so, yeah, we just copy it exactly in this order. Although, notably, well, I guess we copy it in opposite order because, no, that's, no, okay. I mean, it's sort of the opposite memory order from what I have listed here, where this value is actually listed first at the lowest memory address at 24C, and this one is highest at 26.0, but I'm not going to worry about that at the moment, because I also noticed that the result of this indexing does take one of these numbers. You know, that is interesting. So this will start at 0. 284 starts at 0. Come down here, 0 is not greater than 5. So we come down here, and 0 times 4 is 0, so RBP minus 260. So we are indexing into that first D word. But then on the next iteration, because we're adding 1 to 284, come back through, Rax is now 1. So that is RBP plus 4 minus 260. So that'll be minus 25C. Yeah, okay. Right. So we are moving to higher memory addresses. I forget because these are RBP minus. So this is actually at the lowest address. So this ordering is fine. Okay. So we've got the data. I think I need to run through this in GDB to see what the effect of calling rand and then doing this division is, so that I'm not going to like recreate all of this in Python. We're just going to see what EDX is after this sub instruction finishes. Okay, and got to disassemble main. It's a pretty big function, unfortunately, but this is pretty like recognizable. So I'm just going to put the breakpoint on 345. Main plus 345. Then we're going to run it, and we're going to look at what EDX is. Oh, you know what? I also want to put it on rand right after the rand call. So right here at 308. So that on 308, we're going to look at EAX, and then it'll do all of its stuff, and we'll see what EDX is. So C for no, R for run. Okay, so EAX right now is this value. Just gonna do like, put them in here for the moment. Okay, and then we can see what we end up with in RDX is 0. Is that right? Interesting. I mean, maybe I am seeing the wrong thing, but RDX is the thing that gets used for subtracting from EAX. So we load the value of that D word into EAX using the index from 284. So like if we step 1, Rax is now 0 because our current index is 0. Then we use that and we load the 79, which is the first D word in our chunk of data, our array of D words basically. And now we are going to subtract RDX from it, or EDX technically, which is 0. So that's interesting to me, that ended up being 0. Okay, we'll continue. EAX is this value. And RDX is 5 now. Especially interesting. Maybe the maybe what I thought was a division is not. Maybe it's a modulo. It's probably modulo or modulo. Yeah. Let's see. And RDX is 2. Okay. And 0 again. Yeah. Interesting that EAX changed as we went through this. I guess that's fine. That's not of any consequence. But yeah, RDX was 0 out of that. We get this. This will be, I guess, the last one. And it's 2 from that. Okay. Why do we get another time around? Is my math wrong? Guess we do it 6 times. 0 through, oh yeah, okay. And that was a -1? What the heck? Okay. Let's run it again. We get this number. x is 2. And this number gets us, of 3. I don't get what the -1 result is about, to be honest. Okay, so we can get 6. Okay. Very interesting. So let's look at these as decimal numbers. Okay, and that had a 0. Whereas that was 5. What's this? Comes in as 0. What is this a factor of? Like, no. Right? Okay. We haven't seen anything larger than 6, which is interesting. I guess it's 9. So we just haven't seen 7, 8 by coincidence. Right, whereas if we do this number modulo 9, we get 5. So, well, that's we do subtract 1 from it. So these would be modulo 10, I guess. And then minus the 1. Yeah. Okay. So that's how we get the -1. Okay. So this operation takes the random number, does modulo 10, and then subtracts 1 from it. And then it does that 6 times, modifying, oops, I don't know what I did there. Modifying each of these 6 values once. So we go through each of them and we subtract, we subtract the random number modulo 10 minus 1 from it. So anywhere from -1 to, oh, and we get a different random number each time, each iteration through. So each of those are modified by a different random number, and we subtract, so anywhere from -1 to 8 I guess. Because we could get 9, 0 through 9, and then subtract 1 from it. So -1 through 8. Okay. Then again, what we do is we sum all of these numbers. And I think what we could do is I could do it in Python and just like probably mask off the lower 32 bits of whatever the number is, and then we would get the sum of these without the modifications. We could also just do it in GDB and skip this whole loop. That's easy enough. So yeah, then the sum of those numbers, which have been randomly modified based on the known kind of seed value, can then be our guess. So I was talking about how we could do this if we have our clock synchronized and we know that we are running our version of the code in the same second as the remote machine's version of the code. And we probably still could go that route. But again, that assumes that the CTF is designed around allowing us to synchronize our clocks. There might be a way to simply brute force this, because the impact of the random number generator is like minimized because of the modulo operation and stuff. Like the range coming out of this algorithm is not 32 bits, basically. I think that's the right term. Maybe I think the domain is the input and the range is the output of a function. Again, my math skills are pretty low tier math skills. But in general, we could work out what the potential values are. So we're going to sum all of these ultimately. So the net effect of all the random modifications that we're doing should be just the net sum, just the sum of all those random values after doing the modulo -1 operation. Because I think maybe there is something in, I mean, these are small enough numbers. I don't know. I think basically what I'm worried about is like maybe the sum of this will, overflow a 32-bit value in such a way that that the net impact of all the random modifications will not be as simple as if we just sum the random modifications. But I think it's worth it to give it a shot, let's say, or at least to like play out what the range of possible random modifications are. So if we know we're doing it 6 times, so you have 6 times a range of -1 to 5 to 8, and these are each subtracted actually. So what we really have is on the low end, if we get a positive 8 each time out of the modulo 10 minus 1 operation, we get the highest value we can, then we will have a negative 48 total. If we have the highest value, well, okay, so we could do negative 48. Yeah, I think it's every single possible value between negative 48 and positive 6. Because if we get the negative 1 each time, subtracting that then means we're just adding 6. So on any given attempt, we have a 1 in 54 chance of being correct. Believe. Which gives us, you know, roughly 2% odds. I mean, if we run it enough times, then we should hit on that, I'd say. Especially if we use the same number each time. I mean, I guess it doesn't really matter, but let's say we just do the sum. Or let's say we run through it, right? And we look at one of these values. And we just see what the sum total is that gets moved into EAX here. Store that, and then we just run it and try to input that number on every iteration. And if it prints something to us, then it prints something. Otherwise, we run it again. Yeah, let's give that a shot. Okay. So I'm going to run it in GDB again. Going to disassemble main. We're looking for the move, compare, jump not equal. So 288, yeah. So after that move, plus 453. And run it. And then what's in EAX? Why is EAX 0 right now? Oh, right, okay. Because I want what's at RBP minus. So we want a ZW of RBP minus 280. Is that value? Interesting. Okay. Run it again. Let's do that. And what do we have? It's pretty similar. FE7C9 versus FE7C5. Okay, so let's just use 7C9, and we'll just call it again and again until we happen to hit that, and see if this will work. It's not really I guess it's not the intended solution. And I don't, maybe the CTF says don't brute force this one. Maybe the challenge developers have asked you not to, but I really feel like they've created a challenge that is amenable to brute forcing more than your average challenge. So we're also going to keep track of how many tries it took. Okay. And what was the string? Lucky number, so it's this. And let's do it without the while for right now. I'm gonna send line answer and print target.receive all. Okay, the reason I'm doing it just the once, not in the loop, and printing out the receive all is I want to see what it looks like when it fails, because it didn't look like it printed anything out, but it might have printed out a single new line character. Oh, I need to make that a string. Okay, so it just has a empty bytes. Okay, so real quick, yeah, we can just compare it against empty bytes. Okay. So do that, and then we'll get the result, and we'll say if res does not equal the empty bytes, we'll decode it and print that, and we'll break. Otherwise, try plus equals 1. And I'm going to start it at 1 because we're always going to do at least one try. So yeah, I think we can do it that way. Ooh, I need to keep forgetting about that. Guess we can do with context.local log level equals error. Right. We'll see if our odds are too bad for this to work in any reasonable amount of time. It's also, oh, there we go. So we needed 4,500 tries, which is, it's more than I thought, if only because maybe my math about the 54 is wrong. There's a range of 54, but it might be that you have a bunch of different ways of getting those 45 or 54 different values, and then the probabilities are higher than that. There's only one way to get negative 48 and only one way to get positive 6, but there's probably a bunch of different ways to get, 0 and negative 10 and stuff. So okay, my probabilities was poorly thought out on that front, so it's not nearly as high a chance as what I was thinking with the 154. Run it again, see how long it takes the second time. But yeah, I guess with 4,500, that's like more brute forcing than you would really want to do in a CTF, I would think. At least I would be cautious about that, just from the standpoint of like, am I DOSing this challenge? Am I preventing other people from accessing the challenge because I am hammering the server so much? with the network traffic needed to run it this many times. Granted, you could do a little bit of rate limiting, and I don't think that this solution becomes less effective if you rate limit. It just takes longer, but you could absolutely still brute force it, and so that one took 10,000 tries. So the 4500 was probably a lucky one then. But let's say you were in the CTF and you came up with a solution and you knew there was probably a better way to go. See that? I mean, it's, I don't know what the range is on this, and I'm bad enough at math that I'll have to ask a friend to give me the right probability calculation. But one way to go about it would be to simply limit yourself to, once every, if you do it once a second, how many seconds is 10,000? Or how long is 10,000 seconds? Sure. I could do a Wolfram Alpha, but it's just kind of longer than I want. So, if you did it once every second, even that long, significantly longer sequence that we just saw would only take about 3 hours of hitting that server. And then I feel like once every second, once every 2 seconds, if you want to be really nice, I feel like is not really hammering the service enough to prevent other people from using it. Assuming that what you're doing, like depending on how well that machine is stood up, it might crash. And if you are actually crashing the machine, then probably the CTF organizers will mention it and be like, hey, stop doing that. Or if they simply are like, we really don't want you to try to solve this through brute forcing, then fine, don't do it that way. But otherwise, I would say, I don't know, go for it. They've designed a challenge that's amenable to brute forcing ultimately, insofar as the potential range of possible valid guesses is small enough that you could just keep hitting it until you get a random value that lines up with your guess. And what I would probably go this route in a CTF. Like if I were a little bit better at this, I would suss out what was going on, realize, okay, it's going to be one of a certain number of potential values. Just run it once, get one of the potential values, and then let this run in the background with some kind of rate limiting to be nice. And, eventually we'll get the flag on that one while I'm working on other challenges. So you just have it going in the background. You're not waiting for 3 hours, not doing anything. But I think the more intended solution would be similar to what they did on the previous one. If you can get your clock synchronized properly, then you could basically run through their logic yourself and work out what the sum of that is. I don't feel like doing it, to be honest. But let's look at what they wrote, because that's probably what they did. So yeah, they did their own, seed it with time 0 while I less than 6, go through, do the rand mod 10 minus 1, do the modification by subtracting that value, sum it all, and then print out the thing, and then they get it on the first try. So same deal, but again, entirely dependent on time 0 coming back with the same value on your machine as it does on the target machine. Not at all guaranteed, unless that's what the CTF organizers wanted you to do. All right, so we've been going through these pretty quickly. Potentially that's because either there's not a lot of different ways that the bad seed kind of issue can come out, or because this exact nature of bad seed is the only one that's really amenable to a CTF challenge. I could definitely see other ways of having a poor random value situation being a vulnerability, but those being only really like something that an expert, somebody with, you know, much better math skills than myself could actually work out. And you know, that's assuming that they can work it out in a weekend or whatever for a CTF. So it's entirely possible that this is the only category of bad seed type vulnerabilities that we have in the CTF challenges here. So we might just see another one of these calling SRAN time situations. And in that case, you know, hopefully I can get through all of them right now. And then on the next stream, we'll go into the symbolic execution ones, which are, those seem more interesting to me, and are certainly more in a category that I am, or more using a, I mean, I've never really been able to use anger. I've tried once and got real confused real quickly. So I'm kind of excited to give those a shot, maybe on Wednesday, or it'll be Wednesday for me at least. And we have a flag file, so I'll output our flag. And then I forgot, but it hasn't been necessary to do like check sec and all of that on these, because again, I don't think we're doing a real exploit. Maybe there's one way that you could sort of make these challenges more difficult is if you had to do a real binary exploit with wrap chain, or even just a shell code on the stack kind of situation, except that your input was modified by something resulting from calling rand, basically, in which case you would need to be able to predict the seed properly through whatever techniques we were just using, and then use that to mangle your input in just the right way. Like, you could definitely layer this on top of some existing kind of pwnable challenge to add another layer of annoyance and difficulty, which I'm sure everybody in the CTF would be just delighted for. And in fact, if that's the challenge here, I'm gonna honestly be a little annoyed. Okay, so we're calling time 0 again, storing that in, and then using that as the parameter to SRAN. So again, we got the exact same thing as the previous two. We do have a loop here. Okay, so we start out with 0, and we're going to loop, what is that? We're going to loop 50 times. Okay. It's called rand. We move that value into EDX and multiply. Is this another? Looks like this might be another either division or modulo. I guess modulo makes the most sense. I don't know. You could do integer division, and you just want to do the non-remainder portion. Let's see. So then I guess at the end of it, we've got yeah, I guess EAX is what we get at the output of this chunk. And then we multiply that by 100. And So yeah, we do something with the random number, modulo or whatever. Then we multiply that value by 100 and we subtract the original random number from, we subtract that from the original random number. So that's interesting. Maybe we divide it by 100, then multiply by 100 and subtract it. I don't know. We'll find out. We'll run it in GDB just to like see what the result is. And then store that back into 454. And what do we have from 45C? Oh, that's our index number. Okay. And then we print out that many days without incident, I guess. And that being the index number. So we'll start with 0, I guess, and then we'll do 1, 2, 3, etc. And it takes some input from us. It prints what into %? So there's a string at 200 hex in the local stack frame, and we are going to print our whatever random number calculated here is into there. So we get it as a string, I guess. And then we take a string of 10 characters, scanf, and we get rid of the /n that's in there, apparently, with strtoke. And we then compare those two strings. That's an interesting way to achieve the comparison, because we could scan this into a number, but we're scanning 10 digits. So we're getting 10 digits typed in and comparing that using string compare against whatever number we were able to get from whatever the random generated calculation is. And if they're equal, okay. Interesting. So this could be the same as our first challenge, I think. So when we compare and they're not equal, then we get an error message basically, and it says this is the string that you should have given us. So it prints what it had randomly generated and then exits. And we have to do that 50 times, which is definitely a lot. But I mean, in theory, with Python, it shouldn't be a big issue to generate 50 of those sub processes. You'd have to turn off the logging because it would be kind of spammy in the terminal, but should be able to do that, and then just one for each time, and we record what the next response is for each one. So doable. And then yeah, and if we get through all 50, then it prints the flag for us. Seems fine to me. Obviously, again, we could do the work of, assuming we had synchronized clocks, then we could repeat this whole process. But I'm going to be lazy about it. Because because why not? What do we call it? Prepared. Okay, so let me run it once just to double check that I know. Yeah. Okay, interesting. They seem like pretty small numbers, so I guess it is, I don't know, maybe my Julo 100 or something. Okay. So store all of the correct inputs into an array. And well, the length, actually, we need to do, why don't we do it this way? All right, so we'll get our list of processes, and then correct is going to be an empty array. So we'll get something from that array. Doesn't really matter which one we get, I think. And it's going to print out a bunch of stuff. So we'll get through the end of the new line and then do proc dot send line. What are we gonna do? Need to just leave this open. What is it, rand int? Just give me like a simpler, there we go, okay. Sure. Random dot, or we'll just do rand int 100. Okay, so we're going to receive everything up until this bit, and then we will get whatever the output should have been. We'll skip the period. We'll get that as an integer, and then we'll put that into corrects. All right, and then we'll run it one last time. I'm gonna see how long correct is, and then we'll say proc.receive until, and proc.sendLine. Actually, we can do this as and I think that's everything we need then. I need to for sure do like with context. Find the function up here just in case that matters. Flag level equals error. No decode, huh? See if anything works from this. It's taking longer than I anticipated already. Not liking this situation. I mean, it's doing the SRAN stuff first, right? So we are, what are we waiting on here? Receive until used. Let's do this. See if we're even getting, oh, that's weird. It worked really quickly that time. Something must have just broken. Get EOF now? Yeah, why is that? Sometimes it works fine. Other times we get an EOF. I don't know. That's weird. And then this time it's just waiting forever. Yeah, I don't know. It's a little bit finicky based on, I guess, the fact that we are starting up a ton of these processes and maybe some of them are dying while waiting or something. That's unclear to me. But if we get the ability to run through all 50 of them, then we've recorded all of the correct inputs. And if we can do that within a single second. That being said, this is probably also not a particularly realistic way of solving it for a CTF. At least not with Pwn tools, because we would if it's on a remote computer, then we would need to open up 50 connections that would trigger running that program simultaneously, or at least like we'd have to open them all up within the same second, because we need all 50 of them to have the same random seed, or I guess 51. And that seems more tenuous than how we can do it locally here. So the synchronized clocks and predicting what the input needs to be based on rewriting the program locally in C, that solve.c approach that they've used in all three of the challenges in this segment, seems more like what was the intended solution, I would say. That's just my guess. Because otherwise I'm going to have to trigger the remote machine to run 50 copies of this process all within the same second, and then be able to run through all of them before the last one is timed out. And you could do that probably. Like if you started all, and I keep saying 50, but it's 51, I guess. If you start all 51 connections, you select the first connection, you send a guess, it's wrong, you get back the result, and then on all of the remaining 50, you send the correct thing. Now all 50 of those have moved to the second iteration of the loop. You pick the first one again, make an incorrect guess. It says no. Oh, you know what? Some of these probably failed because I happened to guess correctly, basically. I was waiting for the incorrect guess message, and I actually did guess correctly on this one for whatever reason. So that's probably what that was. That just occurred to me. So, yeah, if you send to all of the connections whatever the correct next input was that you just found out by burning one of the connections, basically, that might work fast enough to keep all of those connections alive, and you might be able to do it within a short amount of time. So I mean, that's definitely a solution that I would attempt if it occurred to me that that would be faster than recreating this code myself and trying to make sure that the clock synchronization stuff was happening properly. But if we could do the clock synchronization stuff, if I was certain that that could work, then I think totally doable to get it here. And I mean, they must have done it during the CTF because they've got like what the real flag is. So yeah, they're modulo 100. Yeah. So I don't know. I'm assuming then either, they had to have had the clocks synchronized properly through some means. It just, maybe that is like, in most cases, they're going to be synchronized. Maybe I'm assuming that it's more rare than it needs to be, but like the time that I have here is like a couple of minutes off of the time that I have on my clock, on my phone rather. So my phone is like probably says it's 9 a.m. right now, Seattle time, or in my case says it's like 11 p.m. Local time. So, if my phone and my computer are off by multiple minutes, why should I assume that this target computer is exactly the same time as my computer to the second, which is what is needed for this to work? So, and they don't mention anywhere in here that they had to talk to the people running the CTF to, make sure that they had the exact time. The program itself doesn't print out the time or anything, so I don't know. I mean, that's something that I might even like put an issue on this GitHub repo asking like, hey, when you solve this at Sunshine CTF 2017, because again, they have the real, I don't think they made up this flag, so I'm assuming that this write-up involves this is the write-up they did for having solved it at the actual CTF. Like, just, hey, was there a point at which you had to talk with them to make sure that your clock was synchronized? Because it's entirely possible that how I'm thinking about this is wrong. Maybe time somehow doesn't depend on clock synchronization in order for this, their time function call to work the same as my time function call, basically. I don't know. Anyways, I've gone through all of the ones in the bad seed category. Basically the same challenge every time, different ways of, putting it in there. This one required you to, be able to do it 50 times in a row. But I think if you can do it twice in a row, which was necessary for H3, or rather, actually, you only need to do it once for H3 time. If you can do it once, you can do it 50 times. Basically, it's the same technique. And then Tux Talk Show, was a slight modification on that to the point where I just went with a brute force solution because they their implementation. The randomness was so minimal that you could really brute force it in a reasonable amount of time. But that's it for that category. And on Wednesday, we're going to come in and work on Z3 and symbolic execution. So I've done stuff with Z3 before and I've done like at least one thing, maybe two things. I don't remember completely. But I remember having a situation where there was just like a whole mess of assembly code and the just popping that into Z3, or I say pop that into Z3 like it was a super simple thing, but like converting the assembly code into equivalent Z3 logic instructions or whatever. I was able to run that and get inputs that would be correct to get the proper output. So these will probably be in the category of reversing more than at least the Z3 parts. I don't know about the symbolic execution stuff, but in each of these cases, you are effectively trying to work out what inputs would give you a specific output, because you can see what the output needs to be in order for the program to run properly. And by run properly, I mean like display the flag. Either the flag is hidden inside of the program, or if you give the right input, it does a check and then loads the flag from a file, in which case it would be closer to a pwnable. But again, you're not really doing an exploit on it, I think. So in either of those cases, you are trying to figure out what the proper input is, and the search space, so to speak, for what the proper input is very large, but you can use these tools to very quickly, using the algorithms that are in those tools, you very quickly narrow down that search space and actually can, search it in a matter of minutes rather than thousands of years or whatever if you did the most brute force approach possible. I believe that is the idea. Z3 is the one that I understand the concepts behind a little bit more. Symbolic execution, I only understand it at the highest possible levels of like. I can see how it almost feels like a forwards approach, whereas Z3 is maybe the backwards approach. And that that could be a very bad characterization because again I'm not super familiar with that stuff. So we'll dive into it on Wednesday with me sort of fumbling about and maybe learning some stuff on stream, which has not been the main way that these have played out, but I don't know. We'll see. Maybe I'll do the research ahead of time. So if you were in here watching, this one's been a pretty quiet stream. Might just be the difference in time. Might be the fact that I took so much time off in the the past week and a half. But if you were here, thank you for watching. If you're watching the VOD, thank you for watching that as well. And I'm just gonna sign off now. Okay, I'm really gonna sign off now. OBS died, so that's probably, you saw the stream die for a second.